April 2026. Four astronauts settle into their seats aboard the Artemis 2 spacecraft. The engines roar to life, sending a low, rumbling vibration through the massive structure, through the concrete of the launch pad, and deep into the ground. This isn't just another cargo run to orbit. Humanity is closing a 50-year gap and finally stepping back onto its 8th continent. Standing here on solid Earth, it's hard to grasp the scale of this leap. Take the International Space Station. It orbits just 250 miles above us. That's like driving from New York to Philadelphia, a couple of hours on a good highway. Artemis 2, though, is headed to a destination 400,000 kilometers away. That's 1,000 times farther. Beyond the capsule's thin walls lies an abyss of absolute cold and harsh radiation, where temperatures plunge to minus 270 degrees. The trip to the moon takes just 3 days, but for those 72 hours, the crew will be trapped inside a cramped metal shell, surrounded by vacuum, where one mistake can mean death. And they're not heading to some lifeless rock drifting in darkness. The moon is indeed 4 times smaller than Earth, but it's far larger than Ceres and comparable to Mercury. It's a fully formed world with rugged terrain, a turbulent geological past, and hidden resources. This massive sphere, frozen forever in Earth's gravitational grip, waits for those brave enough to cross this icy ocean of emptiness. From childhood, our view of the moon, the world right next door, has been distorted. In this episode, we'll uncover why our eyes deceive us every night, hiding the moon's true face. Step by step, we'll piece together the story of the first detailed survey of lunar resources, from Renaissance sketches to the formulas of a dreamer from Kaluga. We'll see how pure mathematics built the first bridge across the vast emptiness between planets. And we'll dive into a separate mystery, the biological traces humans left there 50 years ago. Scientists are still wrestling with the question, how well can Earth life survive in a completely alien environment? The moon stands as the only satellite in the solar system whose geography you can explore in detail with the naked eye, from right here on Earth. On every clear night, a striking disk appears in the sky. Dark patches of ancient seas sit side by side with bright highlands scarred by craters. We've grown used to seeing the moon as strictly monochrome, ashen gray, like a faded photograph or a slab of concrete. But that's just a large-scale physiological illusion baked into our anatomy. In reality, the moon is colorful. Those vast plains, frozen rivers of ancient lava that astronomers call seas, are made of heavy basalt, giving them a distinct bluish tint. The ancient continental shields looming above the lava fields glow with yellow-green hues thanks to minerals like olivine and pyroxene. The moon's true palette is far richer than what we see. These warm and cool tones reveal its chemical makeup, but our biology keeps us from noticing. At night, we see the moon in shades of gray because only our rod cells work in the dark. These photoreceptors are incredibly sensitive to light, but completely colorblind. The cones, which detect red, blue, and green, need bright sunlight. They simply shut down at twilight. So, we're viewing this mineral-rich world through our own built-in black and white filter. And the dazzling glow of the full moon? That's another optical illusion. The moon's reflectivity, or albedo, is actually very low, about the same as fresh, dark asphalt. It absorbs nearly all the sunlight that hits it, bouncing back only about 12%. It looks so bright to us only because it hangs against the pitch-black backdrop of space, which reflects no light at all. Place this yellowish-blue sphere in our daytime sky, next to white clouds, and it would turn into a forbidding, dark blotch. Once people realized that the glowing object above them wasn't some mystical light, but a real, physical place, thinkers of the past immediately set out to assess its resources from a distance. This wasn't cartography for curiosity's sake. It was the first thorough inventory of that elusive 8th continent, finally within our reach. Leonardo da Vinci led the way. He didn't just copy the patches of light in the sky, he studied the nature of shadows, how light fell across uneven terrain, and how mass was distributed. His sketches marked the first effort to portray a celestial body as a geological landscape. A century later, English physicist William Gilbert created an even more precise map of the surface, without using a telescope at all. Relying solely on his extraordinary vision and painstaking analysis night after night, he mapped every rise and fall of the terrain. Gilbert identified areas with varying reflectivity, essentially laying down the first navigation markers for explorers, centuries before rocket engines ever appeared on blueprints. Once the land was charted, curiosity took over. People wanted to reach these places and uncover their secrets. Jules Verne proposed the most direct and brutal method, a giant cannon buried deep in the earth. The idea was elegant in its simplicity, but physics dealt it a harsh blow. Verne's project proved impossible. Deadly geoforces would crush anyone inside. To break free from Earth's gravity and head toward the satellite, the projectile had to reach escape velocity the instant it fired. Inside the barrel, it would face a brutal acceleration in a split second. This force would instantly crush the crew into an unrecognizable mass, pulverizing bones and organs before the capsule even left the muzzle. Verne's moon projectile stayed a poetic metaphor, a physical trap in reality. Overcoming Earth's pull demanded a completely different approach. A machine that could build speed gradually, pushing meter by meter through thick atmospheric layers while carefully protecting the fragile life inside its shell. The answer didn't come from cutting-edge European labs, wealthy American universities, or top city engineers. The solution to the most challenging orbital problem, one that had stumped the brightest minds on Earth, was born in a modest wooden house in the provincial town of Kaluga. Konstantin Tsiolkovsky was the first to mathematically prove that reaching space required multi-stage rockets. In his notes, he called them rocket trains. The brilliance of his idea lay in its simplicity. As the rocket climbs, it would shed empty fuel tanks one after another. This approach lightened the craft step by step, allowing it to ramp up speed dramatically without wasting precious fuel accelerating spent stages. Complex differential equations lined up in neat rows across cheap paper. They flawlessly described mass flow, the thrust of scorching gases, and the resistance of the atmosphere. The paradox of this milestone hits with real drama. Tsiolkovsky was almost completely deaf, a schoolteacher who lost his hearing as a child to scarlet fever. That illness cut him off from the familiar sounds of Earth. He couldn't hear the clatter of hooves on dusty streets, birds chirping in the morning, or leaves rustling outside his window. His world sank into a deep, impenetrable silence. And it was in this isolation, far from the constant noise of everyday life, that his mind broke free beyond the stratosphere. A man physically unable to hear the world around him became the only one who truly heard the future roar of orbital engines. In the quiet of his room, he designed a real transportation system to conquer a continent separated by 400,000 kilometers of icy emptiness. His formulas proved absolutely accurate. Pure mathematics confidently cracked open a heavy door to space, right on the pages of ordinary school notebooks. But how did the cold calculations of a reclusive teacher turn into actual metal? And why did rockets, originally built to destroy cities, become the first engines of progress? The path to the stars didn't follow bright scientific ideals. It rose from the ashes of shattered European cities. The first blueprints for real spacecraft didn't smell like fresh ink. They reeked of burnt gunpowder, liquid oxygen, and fear. Every modern space rocket traces its lineage back to one deadly ancestor, the German V-2 ballistic missile. At the end of World War II, engineers of the Third Reich built a weapon of unprecedented destructive power. A 13-ton steel cigar would soar up to a height of 60 miles, crossing into space, only to arc straight down onto the residential neighborhoods of London and Antwerp. It crashed at supersonic speed. First came a deafening explosion that flattened entire streets into dust. Only afterward did the roar of the falling engine reach the ears of those below. When the war ended, the victors rushed not only to claim territory, but to seize the very technologies of death. The United States and the Soviet Union began their race beyond the atmosphere in the exact same way, by testing and directly copying captured German rockets. The American military shipped surviving parts and even the creators of the V-2 to the White Sands testing range in the New Mexico desert. Blazing white sand, scorching sun, and the deafening roar of foreign engines set the stage for the birth of the American space program. Across the ocean, in the vast icy windswept steppes near Astrakhan, Soviet engineers painstakingly rebuilt those same machines at the Kapustin Yar test site, trying to turn enemy steel toward new ambitions. At the helm of this monumental effort in the Soviet Union stood Sergei Korolev. His mind reached for other worlds. He envisioned ships cutting through the void between planets. but his body bore deep scars from Earth's cruelty. Years spent in Stalin's labor camps in Kolyma left permanent damage. Scurvy robbed him of his teeth. Grueling work in gold mines, often below 40 degrees Fahrenheit, drained his life drop by drop. Broken jaws from brutal interrogations healed incorrectly. Korolev lost his health in conditions where mere survival seemed miraculous. This accumulated frailty became a ticking time bomb. In the end, the toll of camp torture and chronic illness cut his life short on the operating table. That premature death would directly halt his chance to complete the Soviet lunar program. The space race kicked off amid a frantic rush, driven by fear of a new nuclear war. Factories, infrastructure, and launch pads weren't built for peaceful exploration of the cosmos. They were designed to secure immediate strategic dominance. Military rockets soon took on a new role. Instead of warheads, they carried the first, still primitive, scientific instruments. In January 1959, the Soviet spacecraft Luna 1 sped toward Earth's natural satellite, aiming to achieve what once seemed impossible. The plan called for a direct hit, a hard crash into the rocky surface. This would prove that interplanetary travel was possible, and that ballistic calculations could be precise. But the technology, built under intense time pressure and constant political stress, failed. A tiny miscalculation in the timing of the radio command to shut off the main engines, just fractions of a second, made all the difference. In the vastness of space, those split seconds turned into a huge gap. The spacecraft missed its target by 6,000 kilometers and slipped forever into the icy void of a heliocentric orbit. A technical blunder almost turned into a global embarrassment. But the Soviet propaganda machine reacted with lightning speed, transforming a navigation error into a major ideological victory. Newspapers around the world ran headlines claiming the USSR had created a new celestial body. Luna 1 had become the first artificial planet. It would now orbit the Sun forever alongside Earth and Mars. And this was an undeniable scientific fact, just an unplanned one. Moreover, as Luna 1 passed by the lifeless gray disk, its onboard magnetometer captured crucial scientific data. The instrument confirmed the Moon lacks a magnetic field. Our neighboring world doesn't have a molten core powering a dynamo. That means its surface remains completely vulnerable to harsh cosmic radiation and the relentless solar wind. A few months later, Luna 2 corrected its predecessor's mistake. A metal sphere slammed into the dusty plain at tremendous speed, carrying banners bearing the Soviet emblem. The impact struck an area now known as the Bay of Rainbows. When it crashed, special spherical capsules exploded, scattering pentagonal steel plates across the alien terrain, marking humanity's first physical footprint on the Moon. But the real engineering breakthrough came that fall. Luna 3 orbited the satellite and, for the first time in history, captured photographs of the Moon's far side, the half forever hidden from our view by a gravitational lock. Capturing the image was only part of the challenge. Digital technology for transmitting photos didn't exist yet. Inside a tiny metal cylinder hurtling through the vacuum of space, a fully automated photolab was hard at work. Engineers had to design a system that developed, fixed, and dried the film right on board, in complete weightlessness. They used special viscous chemicals to keep liquids from flying off as deadly droplets and damaging the electronics. Then a narrow beam of light scanned the developed negative millimeter by millimeter, converting image density into radio signals. Through static and cosmic noise, humanity saw for the first time the cratered, wild terrain of the hidden lunar hemisphere, completely unlike anything before. But taking the next step wasn't just about smashing a piece of metal against rocks. It meant gently landing fragile equipment. To do that, scientists had to solve a fundamental geological mystery, one that would determine the fate of all future missions. Before the first spacecraft touched down, leading experts around the world fiercely debated what lunar soil was actually like. One camp argued the surface was solid, like cooled lava or slag. Another believed billions of years of constant meteor bombardment had ground the top layer into fine powder. They said the Moon was covered by meters of shifting dust. According to this alarming idea, any heavy object would sink without a trace into this dry ocean, burying both equipment and future astronauts forever beneath its surface. Lunar dust is unlike anything we're used to on Earth. Here, wind, rain, and rivers have spent thousands of years rubbing sand grains against each other, smoothing their edges until they're rounded and harmless. The moon has no atmosphere, no moisture, no erosion. Instead, micrometeoroids slam into solid rock at cosmic speeds, melting and shattering it in tiny bursts. This process creates microscopic fragments with razor-sharp, jagged edges. Lunar dust isn't soft beach sand. It's the finest shattered glass, a fierce and relentless abrasive. It can instantly strip protective coatings from metal, jam any moving parts, and embed itself deep in spacesuit fabric, compromising their airtight seals. If inhaled, this powder would act like sandpaper inside the lungs, tearing tissue from within. Charged by relentless solar wind blasts, these glassy particles cling to everything. You can't simply brush them off. Landing delicate electronics on such a harsh, uncharted landscape pushed the limits of the era's technology. The cost of finding a precise answer was staggering. Before Luna 9 succeeded, 10 missions failed. Failures the Soviet leadership chose to keep under tight wraps. 10 times, massive rockets exploded right on the launch pad, engulfing the concrete and burning fuel. They veered off their planned orbits, smashed against rocky cliffs, or simply went silent forever in the cold void, never sending a single byte of valuable data back. Each disaster wiped away months of grueling, around-the-clock work from thousands of people pushing themselves to the brink. Only on the 11th attempt did they finally succeed. In 1966, the Luna 9 spacecraft made the first soft landing ever on another celestial body. Engineers took a radically simple, unconventional approach. Instead of building complex, extendable legs that could get stuck or break on rocks, they enclosed the landing module in sturdy, inflatable cushions. The lander fell like a bouncy ball, bouncing hard several times as it absorbed the impact. Then, the rubber bubble deflated and the hatch opened, revealing intact, unharmed equipment. Metal petals of the antennas unfolded, cameras sent back the first panorama, and the mystery was solved. The surface was firm, and dust didn't bury the metal. This elegant inflatable cushion technique proved so reliable and effective that decades later, it would be used again for future missions to Europa, Jupiter's moon, covered in a thick layer of ice. While automated probes tested the hostile environment, humans prepared for a face-to-face mission. The political stakes soared, pushing engineers on both sides of the ocean to find impossible compromises between crew safety and mission speed. Sending a person into space demanded a rocket more powerful than anything before, and a spacecraft capable of protecting fragile human life amid the void and sudden temperature swings. In this race, every extra gram of spacecraft weight meant burning precious fuel, adding strain to the entire rocket's design. Facing this ruthless weight calculation, American engineers made a fateful decision. They completely abandoned the heavy, bulky two-gas system that maintained atmosphere with nitrogen and oxygen, just like the air we breathe. Instead, they chose to fill the cramped cabin with pure oxygen at reduced pressure. The thin metal hull could handle such low internal pressure, saving hundreds of pounds of crucial weight. But fire physics doesn't forgive attempts to bend nature's laws for political gains. In an environment of pure oxygen, materials change their chemical behavior beyond recognition. What barely smolders or won't burn at all in normal air ignites like gunpowder. Everyday textiles, plastic switches, miles of wire insulation, even the paper flight logs, all turn into perfect fuel, ready to explode. In January 1967, the Apollo 1 crew ran what seemed like routine, completely safe ground tests inside the sealed command module, perched atop a massive rocket on the launch pad. The cabin filled with pure oxygen, pressurized just above atmospheric levels. This tested the hatch seals. Then, a stray spark from a bare wire beneath the commander's seat ignited a chain reaction they couldn't stop. In pure oxygen, fire doesn't just burn, it spreads like a shockwave, instantly engulfing everything in its path. Within fractions of a second, roaring flames consumed the astronauts' suits, melted plastic instrument panels, and filled the cramped capsule with thick, toxic smoke. The temperature inside skyrocketed to 1,000 degrees in an instant. The pressure from the superheated gases surged, locking the inner hatch tight. Designed to open inward, the hatch became impossible to budge. The astronauts couldn't break it open. The Apollo 1 crew burned alive during ground tests, never even leaving the surface. The drive to save weight, simplify systems, and outpace geopolitical rivals turned a high-tech spacecraft into a sealed crematorium. This journey wasn't paved solely with precise calculations or bold engineering breakthroughs. It was forged through twisted metal, shattered hopes, and cut short human lives. Every line in today's safety manuals is written in the blood of test pilots and the burning sweat of specialists pushed to their physical and mental limits. The infrastructure rose amid frantic urgency, driven by a logic of confrontation, where conquering new frontiers served as a display of power. Rockets originally designed to carry nuclear payloads were hastily repurposed to transport fragile scientific instruments and living humans. The system never aimed for careful, long-term exploration of the neighboring world. It demanded immediate records at any cost, and that cost was astronomical even before the first boot pressed into the gray dust, sharp and shattered like broken glass. 10 destroyed spacecraft, lost health for lead engineers, crews incinerated in seconds. Space claimed its victims long before they even left Earth. The victims, twisted metal, and people burned alive were only the price of entry. Space demanded these lives, not to plant political flags, but to unlock a world that shattered all familiar geological laws and forced us to rewrite physics textbooks. For thousands of years, humanity gazed at the night sky and saw the same unchanging silvery disk, patterned with intricate dark spots. Even today, children look at its shape with genuine wonder, seeing a giant lunar rabbit stretching its long ears across the gray plains. Long before telescopes existed, people tried to capture this pattern on paper. Among the archives, a yellowed sketch survives, Leonardo da Vinci's charcoal strokes attempting to record this otherworldly landscape. At the very beginning of the 17th century, English physician William Gilbert created the first detailed map of the moon's surface, relying solely on the naked eye. Modern astronomers genuinely envy Gilbert's extraordinary visual acuity. If we take a high-resolution digital photo of the moon today and deliberately blur the details to match the limits of normal human vision, we end up with exactly the same map Gilbert drew by hand on parchment. He captured the boundaries of the dark areas, what early observers poetically called seas, with stunning accuracy. There's no water in these lunar seas. Those dark patches? They're vast basalt plains, frozen oceans of ancient, heavy magma that erupted from the moon's interior billions of years ago, flooding enormous lowlands. For centuries, scientists believed these basaltic seas covered the moon evenly on all sides. The truth only emerged when the first spacecraft peered beyond the edge of the familiar face. The images sent back of the far side stunned planetary scientists. No seas. Instead, the far side, forever hidden from Earth by an unbreakable gravitational lock, revealed a rugged landscape of bright continents, battered beyond recognition by meteor impacts. The moon is completely asymmetrical. One hemisphere lies beneath a smooth, dark stone, while the other resembles an ancient shield, scarred with countless craters. The near side boasts many seas. The far side has almost none. Two radically different geologic worlds stitched roughly into a single celestial body. This planetary oddity seems to break the laws of physics. When celestial bodies form from a spinning cloud of dust in space, they tend to even out. For a long time, Earth science struggled to explain this phenomenon, until researchers turned their gaze to our own planet. Earth, too, shows a deep asymmetry. Look at a globe from the viewpoint of the Hawaiian Islands, and one hemisphere is almost entirely covered by the endless blue of the Pacific Ocean, with land reduced to tiny archipelago dots. Flip the globe, and the other hemisphere is packed with massive continental plates: Eurasia, Africa, and both Americas. Planets rarely hold perfectly spherical shapes. Take the moon, for example. Its far side's crust formed much thicker. The dense molten magma couldn't break through this heavy stone armor. Meanwhile, on the near side, magma easily cracked the thin crust, spilled onto the surface, and flooded enormous impact craters with black basalt. Photos from orbit only hinted at the scale of this geological anomaly. You can't unravel the story of a celestial body's formation by simply staring at its surface through camera lenses. Cracking the mystery of such a fundamental asymmetry demanded a completely different level of contact. Scientists needed to set foot on those dusty plains. They had to dig deep into the rock, extract samples from beneath the radiation-scorched crust, and analyze the chemical makeup of hidden layers. Sending a human into that hostile environment was too risky at the time, so Soviet scientists chose a different path: building mechanical avatars. If human flesh was too fragile for the vacuum of space, then titanium, aluminum, and radio signals would take its place. This is how the concept of the lunar rover was born. Today we see these machines as classic remotely operated robots, but their original design served a very different purpose. The first Soviet lunar rover was initially planned as an open vehicle for a cosmonaut. Engineers designed it so that a person wearing a bulky spacesuit could stand on a special footboard attached to the side. Holding onto handrails, they would ride across the harsh lunar terrain, traveling from crater to crater. But when the manned program stalled and it became clear that Soviet cosmonauts wouldn't step onto the basalt plains anytime soon, the vehicle underwent a rapid transformation. They converted the driver's spot into a sealed compartment filled with scientific instruments, turning it into a fully autonomous mobile laboratory. The word autonomous hid a massive amount of human effort. The machine couldn't make decisions on its own. It needed the eyes, reflexes, and intuition of operators back on Earth. What's striking is who actually controlled this pinnacle of space engineering. It wasn't astronomers, theoretical physicists, or electronic engineers. Lunar rovers were driven from Earth by former military tank operators, maneuvering an 8-wheeled chassis with independent steering, navigating ruts, judging steep slopes, and traction on loose soil. This was exactly like driving a heavy tank across rough terrain on Earth. The tank operators sat inside a sealed control center in Crimea, staring at dim monitors showing grainy black and white images updated with a delay of several seconds. One wrong flick of a switch, and this multi-ton machine, worth millions of rubles, could have flipped over to the bottom of a crater forever. The skills of these army mechanics, accustomed to sensing the massive size of armored vehicles instinctively, proved more valuable than degrees from prestigious technical universities. These mechanical avatars did more than just leave neat tracks in the dust. Soviet machines pulled off an engineering feat that still commands deep respect from geologists worldwide. They drilled 2 meters into the moon, 2 meters through vacuum-compressed regolith and solid rock, done by an automatic drill without a single human touch. That depth record for penetrating extraterrestrial soil remains unbeaten to this day. Drilling in a perfect vacuum is a physical nightmare. There's no air to cool the drill bit, no liquid to clear away the cuttings. The metal heats up from intense friction, threatening to fuse itself to the rock. Soviet engineers cracked this challenge by designing unique mechanisms that could extract a solid column of soil, preserving the natural order of ancient layers intact. While Soviet robots methodically scraped the surface and drilled boreholes, the United States placed its bet on a completely different approach to exploration. They decided to send human explorers into this frozen void. Landing a person on another world and bringing them safely back demanded a transportation system on an unimaginable, almost biblical scale. The mass of the spacecraft, bulky life support systems, the landing module, and the massive fuel supply for the return trip added up to thousands of tons. First, they had to lift this monstrous weight off Earth's gravity. The need for such colossal payload capacity sparked a historic showdown between 2 engineering giants: the American Saturn V Super Heavy rocket and the Soviet N-1. American engineer Wernher von Braun took an extraordinary technological gamble that completely changed the game. The Saturn V rocket used liquid hydrogen in its upper stages. Hydrogen is the lightest, most energy-dense, and most demanding substance in the universe. To keep it liquid, the tanks had to stay continuously cooled to minus 250 degrees Celsius. Hydrogen seeps through the tiniest microcracks in metal, turns steel as brittle as glass, and could explode violently from the slightest static spark. Taming hydrogen required pioneering new metallurgy and cutting-edge cryogenic engineering. But the reward justified the risk. The hydrogen engine's specific impulse, its efficiency during combustion, surpassed all other rocket fuels. This breakthrough made it possible to launch astonishingly heavy payloads into orbit. Sergei Korolev and the entire Soviet space industry didn't have a hydrogen engine like that. The country's technological base, strained by post-war rebuilding and the nuclear arms race, simply couldn't develop ultra-reliable turbopumps and massive cryogenic tanks for superfluid fuel in such a short time. The Soviet N-1 moon rocket had to rely on traditional kerosene and liquid oxygen instead. Because kerosene was far less efficient, the rocket needed an enormous amount of thrust just to lift itself off the ground. The engineers turned to brute force. They packed the first stage with 30 independent engines, but synchronizing 30 roaring nozzles, controlling flame flows, acoustic shocks, and vibrations in a skyscraper-sized structure, was a challenge that exceeded the computational limits of the automation available back then. This technological gap proved devastating for the Soviet lunar dream. The Soviet N-1 rocket stood on the launch pad 4 times for unmanned test flights, and each time it exploded. One of those blasts became the largest human-made non-nuclear explosion in history. Thousands of tons of kerosene and liquid oxygen poured down onto the launch complex, turning the towers into a sea of molten concrete and twisted, burning metal. The shockwave shattered windows in buildings tens of miles away. The rocket never completed a single successful flight. Buried beneath its wreckage were the hopes of Soviet cosmonauts reaching the moon. At the same time, America's Saturn V stood as a stunning triumph of engineering. This 350-foot tower remains the most powerful and reliable super heavy rocket in human history. It never experienced a single crewed accident. Not one astronaut lost their life during its launches. Meanwhile, the harsh Soviet experience with constantly failing equipment led to a different, crucial innovation, one that saved multiple lives worldwide. Soviet crewed spacecraft featured an emergency escape system at their peak, a small but incredibly powerful solid-fuel rocket. If disaster struck the main rocket on the launch pad or in the thick layers of the atmosphere, this tiny rocket would yank the crew capsule away in a fraction of a second. It carried the astronauts to a safe distance, allowing them to descend by parachute. This system saved Soviet cosmonauts twice during real fiery accidents, proving that in rocketry, a bit of paranoia can save lives. The absolute confidence in the Saturn V's reliability pushed American leaders to take an unprecedented risk. Cold War politics demanded immediate results. In December 1968, Apollo 8 became the first mission in history to send humans toward the moon. It was a bold, raw adventure, daring to the point of recklessness. The flight launched without any prior unmanned tests of the entire lunar system assembled. 3 astronauts climbed atop a giant rocket packed with thousands of tons of cryogenic fuel and shot into the black void. They relied solely on blueprints, math, and trust in their engineers. For the first time, human eyes saw the far side of the moon, scarred by craters, as they flew just 100 kilometers above those lifeless mountains, cut off completely from Earth's radio contact by a wall of lunar rock. But the true physical shock awaited those who had to descend onto the surface itself. Every gram of weight mattered, and engineering pushed the lunar module, a craft designed for a gentle landing, into a Spartan survival cage. The cabin walls were so thin that a strong, accidental strike from a screwdriver could pierce the aluminum shell, instantly releasing precious oxygen into the deadly vacuum. Inside the lunar module, there were no seats, none at all. To save weight, engineers completely removed chairs, heavy metal frames, and padding. The astronauts stood on their feet throughout the entire flight, the complex landing procedure, and all their work inside the cabin. They stayed secured by a complicated system of tension cables and springs, preventing their helmets from hitting the low ceiling during sudden zero-gravity maneuvers. Shoulder to shoulder in the cramped, angular cylinder, peering through tiny triangular windows, they controlled the manual descent. Right beneath their boots, the landing rocket engine roared, burning the last drops of fuel over the looming dusty plain. 2 worlds, 2 opposing research ideologies collided on the surface of the 8th continent. The Soviet Union relied on cold calculation, machine endurance, and remote control, protecting human lives. The United States sent living people into this hostile environment, forcing them to endure massive physical strain, constant fear of mistakes, and extreme exhaustion. These contrasting approaches produced radically different results, leaving behind 2 incomparable figures and 2 very different costs of discovery. 300 grams of soil extracted by reliable Soviet machines, and hundreds of kilograms of rock, for which suited humans wore their hands down to the bone. Every kilogram of lunar soil came at a steep price. Abrasions on their hands, muscle exhaustion, and real physical pain. On Earth, an Apollo spacesuit looked like a massive engineering fortress, a multi-layered shell made from nylon, Teflon, Mylar, Kevlar, and aluminum. Add the life support system, and it weighed nearly 100 kilograms. Even a trained person struggled to take a couple of steps under that load, risking collapse beneath the weight of their own survival suit. But on the moon, where gravity is 6 times weaker, that bulk magically felt like just 16 kilograms. It might seem like this grants incredible freedom and lightness. Yet the laws of physics and inertia don't vanish, and the vacuum of space enforces its own unforgiving rules. A spacesuit isn't just tough clothing protecting against micrometeoroids and radiation. It's basically a sealed mini-ship inflated with pure oxygen to keep blood from boiling in a vacuum. The internal pressure turns the soft fabric into a rigid frame, like an overinflated truck tire. Every simple move, bending an arm, turning around, kneeling, meant fighting against the stiff, pressurized material. The weakest link? The gloves. Pressurized gloves hardened into unbendable blocks. Astronauts had to squeeze their fingers with immense effort, battling reinforced nylon for every motion. Constant friction, sweat, and pressure took a brutal toll. Fingernails peeled away, and beneath them deep bruises filled with blood. Collecting rocks became a long, painful ordeal. Every rock lifted, every stiff camera button pressed, every heavy tool turned sent sharp pain through worn fingertips. Back on Earth, viewers saw only graceful, effortless leaps across a gray plain, never guessing the gloves hid raw skin, dried blood, and massive bruises beneath the surface. Mechanical resistance was only half the problem. The lunar suit hid a far more insidious trap: temperature. The human body acts like a continuous biological reactor. While walking over rough terrain, an astronaut generates about 300 watts of heat. That's as much as a scorching soldering iron or an iron heating up inside a sealed space. On Earth, excess heat escapes easily through sweat and airflow. But in the vacuum of space, there's nowhere for it to go. The multi-layered spacesuit designed to shield against freezing cold becomes a perfect thermos. Without active cooling, an astronaut could suffer a severe heat stroke in just minutes. Engineers had to build a special cooling suit inside the spacesuit, like a mesh undergarment threaded with hundreds of meters of thin plastic tubing. Icy water flowed constantly through these tubes, carrying away excess heat and dumping it into a porous sublimator on the backpack. There, moisture evaporated directly into space. This bulky, uncomfortable system was the only way to survive under the relentless, unfiltered sun. Modern spacesuit designers took this harsh lesson to heart for new lunar missions. The latest suits grew even heavier, up to 130 pounds on Earth, but they gained complex rotary joints and sealed composite bearings. These features adapted to natural biomechanics. Now, astronauts can easily sit in a split or bend down for a dropped tool without risking a fall, wasting oxygen, or scraping their hands raw. This entire documented reality of pushing human limits collides in a strangely ironic way with a wall of absurd conspiracy theories. For decades, skeptics have dissected archival footage, frame by frame, hunting for shadows from spotlights, signs of a studio set, or hidden wires. Their arguments sound confident and rack up millions of views, but uncompromising physics shatters these myths in seconds. The first and most popular claim points to the pitch-black sky, completely starless in every photo. The truth lies in basic optics and the nature of film. The lunar surface bakes under harsh, unfiltered sunlight, which reflects blindingly off the pale regolith. To capture an astronaut in a white spacesuit without turning the frame into a solid white blur, cameras had to use extremely short exposure times. The faint light from distant stars barely registered on the film during those split seconds. If they had taken a long exposure shot to capture the stars, the entire lunar landscape and everyone on it would have turned into a blinding flash. Then there's the flag waving in the vacuum. It looks dynamic in the footage, but the engineers knew that in airless space, regular fabric would just hang limp. To make the flag stand out, they built a horizontal rod into the top of the flagpole and stretched nylon tightly across it. During the cramped transport inside the module, the fabric got heavily creased, and the moon's weak gravity couldn't smooth out those folds. The flag wasn't waving, it had frozen forever in the shape shaped by human hands. The third reason for doubt lies in the astronaut's strange hopping gait. Skeptics argue it's just slow-motion footage on wires. But real lunar biomechanics tell a different story. With gravity about 6 times weaker than Earth's, and a heavy backpack shifting their center of mass high and backward, normal walking becomes physically impossible. Thick boots grip poorly on the loose soil, feet slip, and a wide stride almost always ends with a fall on the back. The astronauts quickly found a better way, moving by hopping on both feet. This kangaroo-style step saved oxygen, conserved energy, and let them maintain balance on the lunar surface, without sinking into the regolith, which felt as dense as cement. Enduring pain, stiffness, and the discomfort of tight suits, people flew to this gray sphere for more than just striking photos with a flag. Their main mission was to transform the lifeless surface into a vast, open-air physics laboratory. One of the toughest and most crucial tasks was setting up ultra-sensitive seismographs. For a long time, a fringe theory circulated among scientists that the moon was hollow, nothing but a cold chunk of space debris. The instruments left behind carefully recorded moonquakes caused by meteorite impacts, thermal shocks, and Earth's gravitational pull. To amplify these signals and probe beneath the surface, departing crews deliberately dropped spent rocket stages and ascent modules back onto the lunar soil. Massive impacts made the moon ring like a bell for hours. By studying how seismic waves travel through the satellite, bending and fading, scientists proved one thing. The moon is not hollow. It has a complex interior with a dense metal core, a viscous mantle, and a solid crust much like Earth's. Another breakthrough came with the installation of laser reflector panels. These simple electronics-free devices are covered in quartz prisms shaped just right. They bounce laser beams straight back to their source no matter the angle of incidence. For decades, the world's top observatories have aimed powerful lasers at the Apollo landing sites. Catching single returning photons, researchers measured the distance to the moon with astonishing accuracy, down to 2 millimeters. These silent reflectors revealed an undeniable truth. Our moon drifts away from Earth by nearly 4 centimeters every year, slowly unwinding the gravitational dance between them. This precision equipment had to survive temperature extremes unlike anything found on Earth. A lunar day lasts almost a month. For 2 weeks, the surface bakes under relentless sunlight, with no atmosphere to shield it. Temperatures near the equator soar to 120 degrees Celsius. Then comes a 2-week night that plunges craters into darkness, where the cold plunges to minus 170. Ordinary earthly metals crack under such swings. Plastics crumble. Lubricants freeze solid. So engineers crafted tools from special alloys, materials tough enough to endure these brutal thermal shocks for years, reliably sending data through the icy void. Scientific ambitions demanded expanding the search area. After all, walking in a heavy suit limited astronauts to a tiny patch around the module. During the last 3 expeditions, they introduced a unique vehicle, the lunar rover. This lightweight, foldable electric car rolled on mesh wheels made from woven piano wire and titanium chevrons, allowing astronauts to travel miles away from the base. But driving on the moon carried deadly risks tied to the planet's very shape. Its small curvature radius means the horizon lies just 2 miles away. On Earth, it's pushed back to about 3 miles. Without familiar landmarks, surrounded by endless identical craters and blinding light, losing your sense of direction became alarmingly easy. The rover gave astronauts freedom, but it also brought new engineering challenges. During one excursion, the astronauts accidentally snapped off the plastic fender above the right wheel. It seemed like a minor problem, but it could have turned catastrophic. The spinning wheel kicked up clouds of harsh, incredibly abrasive dust. Charged lunar soil settled instantly on their spacesuits, gummed up joints, coated radiators with an insulating layer, and threatened to overheat the rover's critical systems. They solved it with human ingenuity, something no machine could match. Using a glossy flight magazine cover and a roll of gray duct tape, the astronauts patched the fender. The rough fix held up through the rough terrain and saved the mission. This newfound mobility unlocked one of the program's most significant discoveries. Harrison Schmitt, a member of Apollo 17's crew, was the only professional geologist ever to set foot on the moon. The others were brilliant test pilots, experts at handling machines, but unable to read the story written in stone. Schmidt's trained eye caught the faintest color shifts, where everyone else saw only a dull gray mass. Since bending over in the bulky suit was nearly impossible, they used long tongs, more like gardening tools, to collect rock samples. Working at the edge of a deep crater, Schmitt spotted an unusual pale fragment. It turned out to be pure anorthosite. Back on Earth, analysis dated it at 4 billion years old, older than any known terrestrial rock at the time. This piece of the original lunar crust, frozen at the dawn of the solar system, offered direct proof that the moon was once entirely covered by an ocean of molten magma. Human intuition and geological expertise outperformed any automated drill by 1,000-fold. Every second spent on the dusty surface drained the astronauts' strength. The brief Apollo missions showcased incredible scientific achievements, but they also revealed a harsh truth. Living beyond Earth would demand a whole new level of comfort and protection from radiation. Returning home didn't mean instant rest or hero's welcome. The first crews pulled from the ocean were sealed inside airtight metal vans and sent straight into strict 3-week quarantines. Scientists and politicians genuinely feared unknown lunar pathogens that could trigger a global disaster. That fear turned out to be unfounded. The moon was utterly sterile. Yet, humans left their own biological footprints behind. As they prepared for liftoff, astronauts ruthlessly tossed out every extra gram. Along with expensive equipment, boots, and cameras, 96 bags of human waste were left behind on the gray dust. This was ordinary trash. Feces, vomit, sealed tightly in plastic. Half a century later, this forced lightning turned into one of the most unexpected biological experiments in space history. Scientists still wonder, did Earth bacteria survive decades of cosmic radiation and extreme temperature swings? There's already one extraordinary case of survival. The Apollo 12 crew landed near the Surveyor 3 probe, which had sat on the moon for several years. They removed parts, including its television camera, and brought them back to Earth. Inside the chamber, to the surprise of biologists, researchers found living terrestrial Staphylococcus bacteria. The bacteria had simply entered a state of suspended animation, surviving vacuum, cold, and radiation, only to come back to life in an Earth lab. The leftover waste bags became an invaluable repository of Earth's DNA, frozen in time, patiently waiting for future explorers. The astronauts returned home, leaving behind rovers, flags, and their footprints on the dust. But the moon's true treasure wasn't on its sunlit surface. It lay hidden in the deep, eternal shadows of its craters. For decades, the darkness of the southern polar craters kept its secrets hidden. It waited until humanity realized that brief tourist trips just weren't enough. Now, the silence of this dead world is breaking, ushered in by a new wave of exploration unlike the political races of the last century. The rules have changed, and the monopoly over space has finally collapsed. China stands alone as the only country to successfully land a spacecraft on the far side of the moon and bring back samples. Pulling off this feat demanded extraordinary ballistic precision. The moon's far side never faces Earth. A massive rocky shield, thousands of kilometers thick, blocks any direct radio signal. Commands sent from mission control would simply crash against the jagged surface. To pilot their lander in this blind zone, Chinese engineers had to launch special relay satellites ahead of time. These satellites entered a complex halo orbit far beyond the moon, forming a fragile digital bridge across the void. When they successfully collected ancient rock from the von Karman crater, it sent a powerful message, heralding the dawn of a new era. The United States met this challenge by building a super-heavy rocket that brings back colossal power. The new American SLS rocket matches the historic Saturn V in sheer strength. It rises like a towering pillar glowing burnt orange. Its solid rocket boosters burn tons of chemical fuel in mere fractions of a second at liftoff. The sound wave from its engines is so intense it can shatter concrete slabs. That's why just seconds before ignition, massive waterfalls of water flood the launch pad, soaking up the acoustic blast. But even the classic thunderous power of government agencies pales next to the private sector's projects. Elon Musk's Starship is so massive that astronauts will need a special elevator just to step onto the surface. This 50-meter cylinder, gleaming with stainless steel, will land on its tail, rising above the gray regolith like a 15-story skyscraper. Climbing down a regular ladder from that height, strapped into a rigid, airtight suit with a shifted center of gravity, would be a death sentence. Engineers are designing external cabins on winches to slowly lower explorers from the upper living quarters to the ground. The scale of these machines, their payload capacity, and their complexity speak volumes. The era of easy strolls is over. Humans are traveling there with heavy construction equipment, massive supplies, and a firm resolve to stay. Staying on this gray sphere means challenging an environment that systematically destroys all biological life. Radiation tears through cells. Micrometeoroids slash the surface like an invisible storm, striking at tens of thousands of kilometers per hour. Temperature swings make metal groan under stress. Surviving on the surface demands enormous energy just to shield the bases. Yet here the satellite offers an unexpected refuge, hidden deep beneath a layer of deadly dust. Temperatures inside the moon's caves hover around a steady 70 degrees Fahrenheit, day and night. This discovery flips our usual image of the moon as either a frozen wasteland or a blazing inferno. Billions of years ago, when the moon's interior still churned, rivers of molten magma carved paths beneath the cooling crust. Once volcanic eruptions stopped, the lava drained away, leaving behind massive hollow tubes, colossal underground tunnels with vaulted ceilings stretching hundreds of feet wide. A thick layer of ancient basalt overhead acts as a perfect natural shield. It blocks harsh cosmic radiation, absorbs the impact of meteorites, and functions like an impeccable geological thermos. Inside these vast chambers, eternal spring quietly reigns. Future colonists won't have to build heavy, multi-meter armored domes on the surface. Instead, they can lower lightweight inflatable living modules into these ancient lava tubes. Once life support systems are activated, nature itself solves the biggest challenge: protection. Not far from these potential shelters at the moon's south pole, scientists discovered vast reserves of water ice. This frozen water, mixed with dust and ancient rock at the bottom of perpetually shadowed craters, places where sunlight never reaches, could reshape the economics of deep space. Water here isn't just water. It supplies oxygen for crews to breathe and hydrogen to fuel rocket engines. These vital resources no longer need to be hauled up from Earth's deep gravity well, saving millions of dollars for every pound shipped. Combining underground shelters with accessible resources turns the moon into more than just a way station. It becomes the perfect safe haven for our entire civilization. The moon offers an ideal spot to preserve Earth's genetic legacy and knowledge archives in case of a global catastrophe. Our home planet is too unstable and vulnerable. Tectonic plates constantly shift continents. Supervolcanoes threaten ash-filled winters. Hurricanes wipe out coastal cities. Biological threats could devastate the biosphere in mere months. Earth's seed vaults, like the famous facility in Svalbard, rely on permafrost that's already starting to thaw due to climate change. The moon is geologically dead, completely sterile and bathed in vacuum. Deep inside its caves, where there are no earthquakes, no oxygen to cause oxidation, and no groundwater, capsules filled with plant seeds, animal DNA samples, and digitized records of human culture could remain perfectly preserved for millions of years. It serves as humanity's backup hard drive, hidden on a stable orbit, safe from any cataclysm on Earth. Building large-scale bases, industrial ice mining operations, and life support systems for the lunar arc will demand an enormous amount of energy. Traditional solar panels won't keep heavy machinery running through the harsh, 2-week-long night when surface temperatures plunge to extreme sub-zero levels. The solution to this fundamental challenge lies literally beneath the astronauts' feet, embedded in the soles of their boots. This is about an incredibly rare isotope, one that costs a fortune on Earth and can only be produced in tiny amounts inside labs. Helium-3 builds up in the upper layer of lunar soil, thanks to the solar wind. Earth stays protected by a thick atmosphere and a strong magnetic field, which deflect charged particles from the sun, keeping them from reaching the surface. The moon has no such shield. For 4.5 billion years, it has taken direct hits from the solar wind, absorbing its particles like a giant sponge. Millions of tons of this priceless isotope are locked in the top layers of the lunar soil, waiting for their moment. The value of this resource is beyond measure. Helium-3 serves as the perfect fuel for nuclear fusion, without the dangers of neutron radiation. Today's nuclear reactors on Earth rely on splitting heavy elements. That process leaves behind mountains of highly toxic radioactive waste. These wastes demand complex storage solutions, sealed away in thick lead containers deep underground. Even cutting-edge fusion experiments using deuterium and tritium slowly destroy themselves. They release streams of fast neutrons that relentlessly bombard the reactor walls, turning the metal brittle and radioactive. The reaction involving a lunar isotope works in a completely different way. It's perfectly clean. It doesn't produce deadly radiation, and all the immense energy released can convert directly into electricity. No bulky, fragile steam turbines needed. Just a few cargo ships loaded with this fuel could power entire continents non-stop for a whole year. The only barrier standing between us and this vast energy bounty lies in the unforgiving laws of physics. To trigger the helium-3 fusion reaction, we need temperatures in the hundreds of millions of degrees, a threshold modern magnetic confinement technology still can't reach. Humans haven't yet figured out how to compress this artificial star matter without it burning right through the walls of magnetic traps. But engineers think in decades. While physicists in Earth-based labs build ever more powerful tokamaks and refine laser systems, space corporations are already designing heavy-duty mining machines. These autonomous giants will crawl slowly across gray plains, heating the top layer of dust, capturing the precious gas released and liquefying it. They'll stockpile vast fuel reserves, ready for the moment when the first commercial fusion reactor finally delivers a steady power flow, ending civilization's dependence on fossil fuels for good. The road to this high-tech future cuts through hard lessons, lost equipment, and a brutal collision with reality. Space doesn't forgive the slightest overconfidence, and the laws of orbital mechanics demand flawless execution of every command. The recent Luna 25 probe crashed because of a software error. But for young engineers, this failure provides crucial experience. A critical malfunction in the engine control system caused the braking burn to last too long. The craft slammed into the ancient surface at high speed, leaving behind only a cloud of dust and a fresh crater. News headlines always paint these events as catastrophic failures. But from the cold logic of rocket engineering, every crash of an unmanned probe is a priceless life-saving crash test. Today's engineers, writing complex code in comfortable research labs, didn't live through the wild lunar race of the 1960s. They never witnessed dozens of early Soviet and American spacecraft explode before technology reached a workable level of reliability. You can't build a safe, fail-proof transport system for living humans based solely on elegant computer simulations. Metal has to bend under stress. Software must fail in unexpected scenarios. Sensitive sensors have to break down when exposed to real vacuum and radiation. Only then do designers get real telemetry, uncover hidden weaknesses, and rewrite safety protocols. Every unmanned station lost today means lives saved for astronauts tomorrow. These intense workouts with steel and code bring us closer to a day when the moon's surface will host a transport infrastructure unlike anything we've ever seen, something truly extraordinary. At this stage, engineers have one clear mission: to eliminate the need to burn thousands of tons of heavy chemical fuel for every launch from the lunar ground. Without an atmosphere, the moon lets rockets accelerate with electric motors along a long ramp, reaching speeds fast enough to break free into space. Engineers call this idea the electromagnetic catapult. Imagine a rail track stretching for miles, laid out over a perfectly flat surface or running along the gentle slope of a massive crater. This system uses superconducting magnets to levitate and accelerate the spacecraft. The capsule glides silently through a complete vacuum, facing zero aerodynamic drag. It picks up speed smoothly and relentlessly, reaching several kilometers per second. At the end of the track, it simply lifts off the rails and shoots into open space without burning a single drop of chemical fuel. A horizontal launch on Earth is impossible. A rocket would burn up in the dense layers of the atmosphere. If you tried to accelerate anything to such monstrous speeds near our planet's surface, air friction would instantly turn it into a blazing plasma meteor. The heat barrier would melt even the toughest titanium and carbon composites in a fraction of a second, tearing the structure apart. The vacuum of the moon elegantly removes this fundamental limit, turning the brutal absence of air from a deadly threat into a grand engineering advantage. Cargo ships could launch from the surface one after another, delivering harvested resources and components of interplanetary stations to orbit with minimal economic cost. Bringing all these unique factors together reveals the true profound meaning behind humanity's return to these silent, gray plains. Basalt caves offer a reliable, safe shelter from the harshness of space. Ancient polar ice provides vital water and fuel components for the expedition. Helium-3 deposits promise an incredible abundance of energy for future generations. And the absolute vacuum creates perfect physical conditions to launch heavy ships without the fiery resistance of an atmosphere. The moon will become the cheapest and most reliable launch pad for missions to Mars and beyond. Its gravity is 6 times weaker than Earth's, a difference that completely changes how spacecraft are built. Massive, clumsy interplanetary cruisers, too heavy to lift from Earth, can be assembled right in lunar orbit. Large components lift off the surface using electromagnetic catapults. Launching to the red planet from a lunar orbital shipyard is like drifting downstream on a calm river. In contrast, every launch from Earth feels like a desperate struggle to escape a deep, pulling gravitational whirlpool, burning thousands of tons of fuel just to clear the first 100 kilometers. The complex, dramatic story of human spaceflight has led us to this moment. From the first crude blueprints, scented with burnt gunpowder and war, to the grueling, hand-bleeding steps in the rigid Apollo spacesuits, everything was just essential preparation. The 8th continent finally sheds its image as a distant, romantic mystery from childhood stories or a prestigious stage for superpower posturing. It transforms into a massive shipyard, a spacious entryway to the truly infinite home we call the universe. People aren't returning there just for striking photos of a frozen flag against the black sky. Humanity is staking its claim on these dusty rocks to build a solid springboard. From here, our civilization will push off, leaving its cramped cradle behind and taking a confident step into the open cosmic abyss.